but he couldn't join us, so we switched. We changed the schedule, and so next speaker will be Luca, and then Zohar will give a remote talk in the afternoon.
Okay, so first, thank Alessandro and Shai and the organizer for this conference, and thank you for inviting me. So my talk today will be based on a rather old work, or few years old, with collaborator DPFL, Anton de la Fuente, Sasha Monin, David Priscalava, and Riccardo Rattazzi, and some work which is hopefully to appear soon with Zorko Margowski. So, okay, I guess in this audience, I don't have to explain, like, we care about understanding CFTs. Understanding CFTs, it's understanding mostly the spectrum of local operators and their correlation functions. And even though the numerical bootstrap was given a lot of information, we also obtained a plethora of analytic results by focusing on regimes with large quantum numbers mostly. So even if the theory is strongly coupled, you have a natural kind of weakly coupled expansion at large spin, a large internal charge where the charge refers to internal symmetries, and large scaling dimensions. And each of these bullet points has some kind of somewhat different physics, but same idea behind the spirit. So why is that we have some simplification, some perturbativity at large quantum numbers? And the basic idea is that in CFTs, you have the state operator correspondence. So local operators map one-to-one to operators to states for the theory quantized in the cylinder, so on R times the sphere. And then, you know, if you have enough physical intuition and if you manage to be clever, you can come up with some simple, not typically semi-classical descriptions for these states. I think the most famous case as inserted in the bootstrap is the case of large spin operators made of two partons. So you take an operator which is somewhat made of two, say, fundamental fields just for the sake of it, and many derivatives in between. They're just a schematic representation. Physically, this quite naturally maps to a state made of two particles spinning fast on the cylinder on the equator. And if you can think of these two particles as quasi-elementary, you can say their energy to leading order will be the energy of a free state. So given by the spin part twice plus twice the mass of the particle, so if you want twice the scale dimension. Now, is this description self-consistent? Well, now you can add interaction on top of the games and see if it's self-consistent. And well, what Aldaim-Maldacena shows is that interactions actually take the form of kind of a Yukawa potential, where the separation delta chi is proportional to the log of J of the spin, and the twist, the gap, is actually given by the twist of the operator exchange in the rho p. And therefore, eventually, the correction are suppressed by 1 over J times the minimal twist exchange in the rho p. What? Yeah, so if the interaction is gauge, actually, you cannot, well, if the interaction is gauge, okay, so the two phi's are not good operators of the CFTs anymore. And then you have a log J in this formula. And yeah, that was harder to show from the bootstrap, but it's also known to be true. But that was actually the case that Aldaim-Maldacena focused mostly on. And remarkably, this simple picture, which is based on a self-consistent but semi-classical picture, was rigorously established by analytic bootstrap, I think first in these two papers of 2012, and since then we've been a remarkable progress in that direction. Okay, so with this introduction in place, let me introduce what I want to do today. So today I want to focus on the O2 critical model in 2+1 dimension. Actually, many of the things I'll say will be more general, but just for the heck of having a specific target. And this theory, well, okay, you all know that this theory is kind of in the Landau-Ginzburg universality class for the critical point. It's a under the first transition. And I want to call OQJ the lowest dimension operator for given charge Q and given spin J. A natural question is from the say bootstrap perspective, what's the scale dimension of this operator as a function of Q and J? So for small Q and J, I think data can only come from numerics, or at least to our best understanding now. I think the state of the art is this paper by, I think, especially by 3 of the people in the audience, maybe more. And so the main talk, we focus on the regime of parametrically large Q or J, where we expect semi-classics to be useful. So Okay, so already in the regime of J to infinity and Q fixed, we expect this operator to be some kind of multi-trace operator. So where there are many fundamental fields separated by a huge number of derivatives. And if these derivatives are sufficient, large enough, then we can think of this as kind of Q-free particles interacting with angular momentum J, and therefore their energy will be given by J plus Q delta phi. If you want, this kind of follows from iterating the analytic bootstrap arguments, even though it's hard to compute corrections from the bootstrap. For Q much larger than 1 and spin order 1, we expect instead the corresponding state to be a superfluid. I'm going to explain this in more detail. And the operator will be something like phi to the Q, but the scale dimension will actually not be linear in Q, as you might expect from free theory, but will go like Q to the 3 half. And I think yesterday Ning showed a very beautiful plot of how this works up to Q equal 2, surprisingly. Yeah, most of the things I'll say actually apply almost verbatim to the 3 model. So, and this talk, okay, so more specifically will be about interpolating in between these 2 regimes via a series of effective field theory and semi-classical arguments by identifying the proper state. Questions for the introduction? Okay. Okay, so this is the overview of my more technical part of the talk. So I'll start reviewing the large charge expansion. I'll then start building up spin and discussing charge spinning operator. And I'll finally comment a bit on the multi-trace perspective from Aldheim-Aldacena viewpoint. And I'll finally summarize. Okay. So for spin 0, the lowest dimension operator of the auto model is not identified with phi to the Q, or whatever you want to call it. It doesn't need to have a name. And it's some state Q. And one property for sure of this state is that the state has charge Q, so therefore it has a homogeneous charge density Q because it's scalar on the cylinder, on the sphere. So now the sphere has a natural radius R, and this charge density introduces a scale mu because Q over R squared is dimensionful, of course. So when this mu is sufficiently large, or when the charge density is sufficiently large, this is a finite density state pretty much as the one we find in nature. So it's a condensed matter state. And we know quite a bunch from condensed matter physics about this state. So the question is, which state is this? Just some state at finite density, which that Poincare is not realized linearly, I think. Yeah. So if you look at 0 temperature finite density states, well, unless there's some experimentalist tuning, some parameter for you, like an external field, there are 2 most common options. One is to have broken U1 symmetry and have what is called a superfluid. One is to have Fermi surfaces, even though they are typically unstable. So we could discuss which one is most generic, but today I said I want to focus on the O2 model. O2 model is a bosonic theory. So clearly the only candidate among these 2 is to think of this as a superfluid. So I'll assume this is the case. You can justify this assumption at large n or in the epsilon expansion if you're unhappy with this genericity argument. Or from a Path integral viewpoint, but I'll just take it as an assumption today. So in field theoretical language, what's a superfluid? So I said a superfluid is something which breaks spontaneously the U1 symmetry. And well, more precisely, the breaking pattern of the superfluid is given by something like I showed there. So you have an Hamiltonian H, a U1 symmetry Q, and you break them to a diagonal combination H bar, H plus mu Q. All this means is that you have a U1 Goldstone boson, but you do not expand it around a trivial profile. You expand it around a profile which goes like linear in time, mu T, plus pi of x, where pi is essentially the true phonon of the superfluid. Okay, so this is an effective. So once I talk about Goldstone boson, I want to hint that you have an effective field theory description. But for this effective field theory description, you have to ask, what about other possible modes? Well, in the simplest possibility, these modes will be gaps by the interaction with the density, which introduces a scale mu, which, as I said, is much larger than the geometric scale of the sphere. Therefore, they will generate expectably gapped at a scale which scales like square root of Q. Of course, there are exceptions to this rule in some theories that have additional symmetries, most notably supersymmetry. But in theories with moduli spaces, so n equal to SUS in 4D mostly, you can argue that you have a full vector multiplet of light operators, but okay, you need additional symmetry for that. In the simplest case, therefore, you have just one Goldstone boson, radial modes are gapped, and clearly the logic is the same one underlying the pion Lagrangian and many other progress in physics, is that we write the Lagrangian as a systematic derivative expansion in derivatives over mu. And yeah, I should give credit actually to Simon Ellerman, Domenico Orlando, Sir Reffert, and Masataka Watanabe for this idea in 2015. Okay, so how do we do that in practice? Okay, so here, okay, the way to write the Lagrangian is to suppose, impose that you have a theory with conformal invariance. You want symmetry on the cylinder. Okay, you can put it on any manifold, but I want to focus on the cylinder because that's where a state operator correspondence. And if you do that, it turns out that the action depends on up to the first subleading order depends only on a finite number of coefficients. A leading order just c dk to the cube. This dk to the cube just means d mu chi to power 3 half. It looks very singular, but you should remember them expanding chi around mu t, so around a non-trivial profile. So when you expand this term in pi for derivatives of pi much smaller than mu, it's actually analytic. And then you have two subleading correction, which depends on the curvature of the manifold. So R is the Ricci scalar or the Riemann, and then so forth so on. Each of these corrections is suppressed by powers of decay. Decay is not identified with mu. So each of these is suppressed by 1 over q expansion. So you see, you do have control over this effective field theory on 1 over q expansion. So the simplest thing you can do, which is not something we typically do in effective field theory, but it's useful in this case, is to compute the energy of the ground state. By the state operator corresponding, it maps to a scaling dimension of the lowest density operator of charge q and spin j equals 0. And that's the result you find. You have some classical piece coming from the effective field theory, where alpha and beta are related to the C, C1, C2 there, which goes like q to the, yeah, so okay, which goes like q to the 3 half, then q to the 1 half, then you have a one loop correction, which is actually remarkably independent of Wilson coefficients, and then subleading terms. Okay. So this is actually how the result that Nick plotted yesterday is derived from effective field theory. Of course, you can do more. You have an effective field theory, so you have control over all the states which are below your cutoff. So the simplest thing you can do is just expand to quadratic order your action and look at the fluctuations. Fluctuations are identified with this field pi, which is just a sound speed. So it's not relativistic because I'm expanding around state that breaks spontaneously Poincare, but it has a sound speed which is fixed by conformal invariance. Famously, the sound speed of fluids is fixed by conformal invariance, is 1 over square root of 2 in the case of 2 plus 1 dimension. And therefore, it has a dispersion relation given by this formula where J is the angular momentum. This gives you non-trivial information about the spectrum because you have the energy of all the state created by this Fock space of phonons correspond to operators. And in particular, you can see that the J equal 1 Fock state is just creating descendants. You can compute either the momentum generators to see this, or just notice that it has omega 1 equal 1. So it's actually not identified with the action of a derivative of this operator. Broken U1. So when you break space-time symmetries, it happens so that you do not need as many Goldstone boson as the number of broken generators. In this case, it happens so that if you break conformal, chi is related to pi in this way. So there is US expander on some background. Yeah, so there is just one Goldstone boson in this theory. Right. And the main message is that for J larger than 1, there are new primaries. And so in particular, you can predict the spectrum of states with spin. Okay, so actually, maybe this is actually the simplest non-trivial prediction of the effective field theory, because kind of the energy of the ground state, it can be argued on some analyticity and locality, respectively, of what is the effective field theory underlying the description. But the spectrum of excitation is really a smoking gun prediction of the superfluid. Okay, so now what can we say? Maybe I'm going a bit fast. So what can we say about spinning operators with charge now that we have this Fock space? Well, the most naive thing to do is to say, okay, as I know I have my superfluid, I have my phonons, so operators with charge Q and spin J, there will be phonons on top of my ground state. So you can look at the energy of one phonon with spin J, and it will grow approximately linear if J is large. You can also imagine looking at n particle state with spin J over n. It's another natural candidate. Again, the energy is approximately linear, but because of this n in the square root, it's slightly larger than a single phonon state. Now you should ask, when can I describe these states within effective field theory? So the single phonon state, of course, it's there as long as the angular momentum is much smaller than the cutoff. So in the simplest case where I don't have weak couplings to complicate my dimension analysis, is J much smaller than square root of Q. N phonons, you can sprinkle them over the sphere. So as long as they are dilute enough, so N much larger than Q, and their individual angular momentum is much below the cutoff, I can trust this state. So in principle, I can trust this description up to J much smaller than Q2A3 alpha if you do the parametrics. And therefore, you get a prediction that at least for sufficiently large J, this should be the energy of your ground state at leading order in Q and J. It's like the ground state energy plus something linear in J. But okay, if this was the end of the story, it would be a bit boring, but we believe it's not. And the main reason why I believe it's not is that that's not what happens in physical superfluids. It's not phonon carrying the spin up to large angular momentum. So, okay. Again, as I said, even though I'm doing CFT, a lot of intuition comes from looking at some condensed matter things, or mostly in this case, Bose-Einstein condensate literature, maybe it's a bit different, called atoms. And the experiment showed that if you put a Bose-Einstein condensate, it's just a fancy name for a superfluid in our language, a state which breaks U1 symmetry, and you make spin the trap, at some point you start developing vortices. You just don't just develop phonons. You have first, here it's such a picture, you have first one vortex, then a bunch. This is not a Dragon Ball. Then even more, and even more, so forth, so on. And so it's natural to expect that something like this should happen also in our case. And the idea is that, can we see that within effective field theory, or make predictions within effective field theory? Okay, so how do you describe vortices in effective field theory? Well, this is again, this is based on some simpler version of particle vortex duality, if you want. And the first thing is technically useful to realize that I can consider a scalar in 2+1 dimension. So my Goldstone boost in 2+1 dimension is actually exactly dual to a gauge field in 2+1 dimension. And the duality explicitly reads like this, where I'm relating the coefficients. The way to match the two sides, is to know that the U1 current on the scalar side maps explicitly to a topological current on the gauge side. So the mapping is actually given by the formula I showed there. This means in particular that the homogeneous charge density of the superfluid maps into a monopole field at the center of the S2. So which in the theta phi coordinates leads like this. So magnetic field B, which is essentially order Q. So now in this description, the cutoff is not square root of Q, it's square root of, well, it's square root of B, which is the same thing as square root of Q. Okay. So, why is this useful? Well, because vortices, what are vortices? Vortices are configuration on which the field is not single valued. And in this description, you can capture them in terms of charged particles. So you introduce word lines of massive particles and couple them minimally to the gauge field. So the QP here, so here this is my superfluid action to leading order, and I'm coupling them to these word lines with QP, which is actually equal to the vorticity you can show. So these vortices, why are massive? Well, they're massive because their mass by dimensional analysis given by the only scale in the game So it's of order of square root of Q. So if you want by conformal invariance, it should be given by the magnetic field, if you want more rigorously. So the dynamics of vortices in a superfluid is the same thing of the dynamics of particles in a strong magnetic field. And we all learned in schools or in university that magnetic particles in a magnetic field, they actually organize in Landau levels with gaps of order B over M. But M is ordered square root of Q, B is ordered Q, so these gaps are ordered cut off. So the physics point actually is that once you want to do this within effective field theory, you can do that, but you have to integrate out all the Landau levels but the first, because they're separated by a cutoff gap. This is called effective field theory for the lowest Landau level, and it's well, it's rather standard in condensed matter. Actually, it's what is based on the quantum Hall literature on. And technically, this just amounts to saying that since they have a strong magnetic field, there is a kinetic time which is first order in the velocity from the minimal coupling to the gauge field, which is leading with respect to the velocity term from here. So you just neglect the second term in this action. So if you want a more classical way of seeing the lowest Landau level, is saying that vortices within effective field theory will be moving slowly, so I can neglect higher powers of the velocity. Okay, so bear with me on one extra slide, then I'll show some results. So just want to give some hints of how you do this analysis. So, okay, so now I have I told you that the problem of studying vortices in a superfluid maps to the problem of studying point charge, point particles in an electromagnetic field on the sphere. So it's an electrostatic problem. And we know how to study this electrostatic problem. The motion of vortices is given just by the drift motion. Electric field will be velocity times magnetic field. There is an extra term if you think of Newton's laws, the mx double dot. But as I said, in the lowest Landau level, I can neglect higher derivatives on the point particles. So to leading order derivatives, that's the equation. There is a Gauss law for the electric field. This is very non-manifest in the scalar picture, but it's very obvious in the dual picture. And where rho is the vortex density. And the coupling here just happens to be is just square root of Q. So E square actually is again, is given by the magnetic field. It's just a redefinition. So the electric field is naturally given by square root of Q eventually divided the distance between the various vortices. So as long as the distances between them are large enough, the electric field is stabilizing with respect to the magnetic field. So we still have effective field theory. And vortices move slowly, as I said at the beginning, 1 over square root of Q. And of course, since I work on the sphere, Gauss' law implies that the sum over all the vorticities should be 0. If I just integrate this equation on the sphere, the left-hand side gives me 0 because of total derivatives, so the right-hand side better gives 0. That's all I'm saying. So, okay, maybe the most important point for you is that if I have a number n of vortices, then I can compute their angular momentum and their energy, and therefore make a prediction for the scale dimension of the corresponding operator. Again, I remind you, I'm using state operator correspondence. And these are the formulas I find. So the leading order is still given by the energy of the superfluid, but then I have a funny log correction, which is proportional to square root of Q, sums over the interaction of the vortices. So Rp and Rq this is actually just the chordal distance on the sphere. So this is just the statement that an Coulomb potential in 2+1 is just a log. So, and log Q, this comes from a funny fact which is called essentially the self-energy of the vortices that need to be cut off at order square root of Q. The angular momentum instead is proportional to, again, R, which is a unit vector on the sphere pointing in the position of the vortex, times Q half, and times the vorticity, of course, because larger vorticity, larger angular momentum. Okay, so even if you fell asleep, maybe I think it should be easy to understand the results, at least intuitively. So, well, if you now start scanning over all possible configuration of vortices, and you assume that in your theory there are vortices of arbitrary charge, which is what to expect to be true in the O2 model, if you want in the by particle vortex duality, then lowest dimensional state with angular momentum between square root of Q and Q is not anymore given by a phonon, but you conclude is given by a vortex anti-vortex pair, which is spinning on the sphere. So the blue line is one vortex, the red line is an anti-vortex, and here I'm plotting the stereographic projection. The reason why they're moving this way is because they are moving with some velocity v, and there is an electric field which repels them, but then you have the VB force of the Lorentz force. And the angular momentum is proportional to their separation, and it ranges between square root of Q and Q essentially. You cannot go below square root of Q because then the separation here becomes very small and you cannot trust anymore the effective field theory. And you can compute the energy, and remarkably is given by the energy of the superfluid ground state, but you have some corrections which are logarithmically enhanced by square root of Q, and you have this log J square over Q, which is fairly non-obvious from other perspective. Questions so far? Well, that's just because when J is Q, the two vortices go north and south pole, and then you cannot displace them further apart. So you have to start looking at configuration with two vortices to go beyond that. So this formula here is just, yeah, that's a good question. Okay. Okay, so this is just a small technicality. All I've been saying so far looks very classical. I just want to point out you can do quantum physics on this state. And the idea is that vortices have coordinates r on the sphere, which are proportional to the individual contribution of the angular momentum. Then it's obvious the quantization, you can do it more properly, will just give you that each vortex coordinate satisfies an SU2 algebra. This is sometimes called fuzzy sphere. I want to just mention it because some of you might know about it. And well, the endpoint result is that there is an obvious way to correct at a quantum level the formula showed before, is just by promoting the J squared to a JJ plus 1 in the log. So rather obvious, but it comes from these formulas. Yes. I'm neglecting it because it's subleading with respect to this logarithmic term, but it's still there. In fact, there are even other square root of Q contribution from the vortex masses that I'm neglecting. So all the formulas I'm showing here, they will be leading order in Q and J, and not to overload slides, I kind of neglected writing corrections. But that's a good point. The Q to 0, no. The Q to 0 doesn't change, not the leading order in J. I don't think there are data on spinning operator with large Q. There are no data about spinning operator with large Q, I think. Well, I don't think even this formula here I showed before wasn't compared until yesterday night by Ning, as far as I understand. So I think it would be first nice to verify this formula here for the phonon, but in principle it should be doable. I think even in weakly coupled models, people didn't compare with these effective field theory predictions, but I know they're doing it now. So yeah, hopefully soon enough, yes, but not yet. The vortex? The vortex is still square root of Q, the cutoff. It comes because there is a magnetic field. I think one is because here I'm not showing higher derivative correction in this action, and this will be suppressed by powers of the magnetic field. So this is pretty much like this scalar description. A more physical way is that vortices are parting in a magnetic field, and the gap of the Landau level is B over M, which is again square root of B. And I cannot trust the higher Landau levels. Okay, I think I'm doing okay with that. Okay, so this is so far till J equal Q. You can go slightly beyond by considering 2 vortex or 3 or 4 vortex configurations and so forth, so on. But if you start doing this analysis, you see that since there is this log Q time, which is enhanced by the vorticities, it's more convenient to have more vortices rather than having one vortex with large vorticity, at least naively. So it's natural to look for configuration with many vortices to go to the regime with angular momentum much larger than Q. It's kind of straightforward to do that. You just, again, you borrow actually for the superfluid trap is done by in the Feynman lectures famously, and essentially an analogous calculation here. You approximate the Vostok distribution with some density rho, and minimize the energy at fixed angular momentum. So it's a classical calculation, and you find that this a number of vortices which unsurprisingly goes like J over Q. And the energy actually has, again, the superfluid energy with some correction, which now goes like J squared over Q to S3 alpha. And this is sometimes called rigid body in the Bose-Einstein condensate literature because it moves with the same speed of with same profile of a rigid body of a sphere. So two things: this formula holds only between J much larger than Q, but also much smaller than Q to S3 alpha. So that's because otherwise vortices become relativistic and the rigid body moves too fast. And the other thing is that you see this subleading term approaches the value of the leading term parametrically when J goes to Q to S3 alpha. That's what you kind of expect, because when you know that, then you know that when the angular momentum becomes large, approaches the scaling dimension, then you should have something which goes like J from the bootstrap. So when J is of order Q to S3 alpha, both these two terms better be of order J. But okay, this still okay. So in principle, this could be the end of the story. You might expect that from now on, the multi-trace bootstrap predictions apply, but we believe, and I'll justify it from two different perspectives, that that's not the case. So the natural question is, what happens beyond this regime in J? So it's actually something very cool happens if you look at experiments again, or simulations, but also actually experiments. So if you take again, let's look again at Bose-Einstein condensate in a trap. The trap now must be quartic, and make it spin fast, much faster than the speed of sound of the phonons. Then at some point, what happens is that the flow vortices stop to develop, and rather you get a rotational flow, but it's actually localized on an annulus, a small annulus, well, which is called giant vortex. And this thing was remarkably realized experimentally, I think, a few years ago. This is a picture, actually, it's not a simulation. There is actually a beautiful non-technical review, like from a popular, in this Physics 2020 issue. So, well, okay, so this happens for Bose-Einstein condensate in a trap. Could this happen also for superfluid on the sphere? Well, we believe it does. And okay, so the natural candidate is to think of a vortex anti-vortex, but with huge vorticity. And again, and the idea is that this, when you exceed Q to S3 alpha, could be the ground state. So let's try to see if this is self-consistent. So the profile just reads like this. So this is essentially a vortex anti-vortex in the scalar description. I went back to a scalar description, it's more convenient here. And it has angular momentum equal LQ. But now I want to go beyond the effective field theory I showed before. So I want this L to be huge, essentially. If you do that, you see that the charge density is positive in a region, but then you have to cut off the effective field theory to be consistent in another region. So essentially you get a picture like this. So here is where you have superfluid density, and here is where you have nothing. And the superfluid is spinning. So this starts looking pretty much like the picture I showed before, where the density was localized in an annulus. Sorry. So, okay, so maybe this is a bit technical. I don't want you to focus too much on it, but now in this regime where J is much, I want to go to J much larger than Q to S3 alpha, and you can relate these parameters mu and L to J and Q. And the main thing is that L over mu is actually very small. So L is almost mu, so that's different than before. Okay. So, okay, so for this picture I'm proposing to be consistent, we should have a consistent effective field theory everywhere. So let me just try to argue that we have a consistent effective field theory everywhere. So if you have some linear sigma model, it's useful to think, for instance, of this d chi-square as a master for the radial mode. So let's try to imagine that this is true for a moment. I can justify it more in detail, but let's imagine this is true. So we should ask, are radial modes gapped everywhere to have effective field theory? Well, the region where you are away from the equator, well, this m square is, you can actually compute it, is mu square minus L square over sine square theta. And essentially, this m square is positive because of this 1 over sine square theta. And you have a huge, and you can interpret this as saying I'm looking at states with large angular momentum. And if you know, if I do that, I have a centrifugal potential. And this actually is gapping out all the excitation. So I'm fine away from the equator. What about the equator? The equator, actually, the mass changes sign, so I have condensation. I have a superfluid, indeed. And then I have to ask, okay, what's the cutoff of the superfluid? The cutoff, of course, is the scale of the radial mode in the simplest theory. So order m, which again, you can compute. It's not obvious, but it's square root of q. And now, but what is the size of this strip? The size of this strip is delta. And again, you can compute is q3 alpha over j. So to have effective field theory, you need that this delta better be much larger than 1 over inverse cutoff. Otherwise, the energies that you localize there, they can never be within effective field theory. Okay, you do this exercise, compare this delta, compare this cutoff, and you find that this happens for q squared much larger than j. Okay, so you seem to have some room, but you're not yet done. There is an extra region I'm not telling you anything about, which is the region of transition between the vacuum and the superfluid density. So, well, here, naively, the mass square is of order 0. And you can actually estimate the size of this region just by saying when does the derivative expansion here break down. And you find that this size actually has this weird scaling, q to the 1/6 over j to the 1/3. But since I want to take j much larger than q, you start to see in this size, oh, it's kind of small. So, well, the natural thing to do in effective field theory whenever you have a small size you cannot describe is to replace it with some effective boundary. Just put some boundary condition for your effective field theory. Again, I won't show you how to do that, it's a bit technical, but order 0 consistency requirement for this to be true is that this size delta bar better be much smaller than the size of this region in the bar. You do this ratio, you compute, and again, it's some power times j over q squared. So you have effective field theory as long as q squared is much larger than j again. So beautifully, you conclude that you have a region, room for doing calculation for j much larger than q to the 3 half, so you exceed the vortex lattice before, but j much smaller than q. Okay, maybe this was a bit technical, but I think it's just to show you that there are many things you have to think about when you do this effective field theory. Huh? Yeah, sorry, q square, of course. Yeah, that this equality, that this inequality doesn't make sense. Thanks. Okay, it's worse. Okay, so let me just show you the result. Okay, so the main reason why we got excited about this is that when you compute the energy in this regime, you find the result which is remarkably very different than the one before, which is now the energy goes linear in J. And that's like what you expect from the multi-twist multi-traces operator, which are separated by many derivatives. So for J clear real, the result approaches this expectation. So it's kind of natural to think of this giant vortex as something in between the bootstrap and the superfluid picture. There are actually corrections which are calculable and still depend on this alpha to leading order. So this is actually a very non-trivial prediction, and it depends on the same coefficients on which the Q to the 3 alpha terms of the superfluid density depended before. Alpha is, so when I showed before the superfluid energy was alpha Q to the 3 alpha plus dot dot dot. So this is the same alpha. So all my, yes. I don't think this is the light cone. I'm going to show in a moment the light cone bootstrap, I think, should break down at q squared over j. Yeah, so it's it's a new phase. It's not the same, but it's natural that it goes in between. But I mean, maybe a word of another nice word is that when q squared becomes of order j, this case like q, which is what you expect, the first light cone correction should be also order q because it's q delta phi. So qualitatively it matches, but it's just a qualitative matching, not quantitative. Well, even more interestingly, I think if you compute the spectrum now, it's a bit of a technical calculation, but it's essentially because since you're moving very fast, the spectrum is approximately chiral to leading order. So you have states with energy gap over which is m plus n, where both m and n are integers. N is positive and m is not, and m corresponds to the change in the angular momentum. And this is precisely what you expect from okay, you can be more careful, but it's precisely what you find by displacing derivatives on a multitrace. Because if I take out a derivative, I lower the energy by 1 unit, so I take m equal -1. If I put the derivative, I increase by 1 unit, and I also increase the angular momentum. I can put a box, and then I do not change the angular momentum, but I change the energy. So this is descent. So this really matches what you would naively guess by just moving derivatives in this multi-twist. So this is also exciting. The n equal 1 is obtained by doing some contraction with epsilon tensor, but it's also there. Again, from the EFT viewpoint, you might be puzzled because you say, but if I take now states with say 2 particle states with m equal -2 and m equal 2, or m equal -3 and m equal 3, it seems like I have a degeneracy of the ground state. So you have to restore the first bleeding correction in q³ over j square. And if you do that, you find that actually the ground state is unique. So there is no issue with effective field theory. There is just a rather small gap that you can compute. So, okay. Questions for? Okay. Okay, so this is mostly what I wanted to say about superfluids. So the last part of my talk will just be about, I told you we have all these different regimes on the superfluid theory. So why from the more, well, Aldheim-Aldacena, I want to say bootstrap perspective, so it's bootstrap intuition, should we expect these regimes to be there up to j order q²? And so this will be really just some comments. It will be slightly less precise. So for j to infinity in q fix, the picture is that the state, the giant vortex should break up into a number of partons, so to say, which are sufficiently separated so that you cannot think anymore of them as some condensate that are spinning on the sphere. And the prediction is essentially by iterating analytic bootstrap, that is the energy is j plus q, the energy of the single particle plus ... But then you have two interactions. And the interaction comes from the potential that these partons exchange between them. So they come from the analytic bootstrap exchange of T mu nu and J mu, essentially, where these are the, so T mu nu and J mu, of course, are the stress tensor and the U1 car, and they are both twist 1. So that's why they're leading. So again, to leading order, the most important exchanges are the nearest neighbor one. And the energy is this Yukawa potential, e to the minus tau, the twist, which is 1, and delta chi, and the delta chi I told you is the spin. Since they are nearest neighbor, it's not the spin, it's the spin of each individual parton, so it's j over q. I have to sum over all of them, so you have a q. So this goes like q² over j. Well, again, so this is kind of your coupling constant, if you want, in this point particle effective field theory. And if you want to trust a single insertion of the potential as a perturbation, V better be much smaller than 1. So this quasi-free dynamics, in other words, holds only as long as the potential or the single insertion of V is much smaller than 1. And therefore, it only holds as long as J is much larger than q². This, again, is beautiful because it agrees with the upper limit of the superfluid theory I derived before from other language. So it might be possible, actually, to resum many insertion of this V and see this giant vortex emerging in some way, but I'm not aware how. But it would be very cool. So, well, there is another piece of consistency. Okay, we verify that the Aldheim-Aldacena picture breaks down at j order q². But now we have to ask, okay, we want the ground state to be some condensation. So better, this interaction better be attractive. Is this true? So I told you before, the interaction comes from one exchange of T mu nu and one of J mu. I think this is clear if you imagine a theory with an ADS dual, even though maybe we don't know it for the O2 model. So this essentially, an ADS dual is an exchange of a graviton, and this is an exchange of a gauge field. So since all the particles have the same charge, the exchange of the gauge field is repulsive, and the graviton exchange is attractive. From the analytic bootstrap perspective, this means that the insertion, the contribution of T mu nu gives a negative contribution to the scaling dimension of the double trace, and the one of J mu gives a repulsive contribution, so a positive contribution. So the question is whether the sum of the two is negative. So this was actually quantified. And again, I'm only looking at nearest neighbors. I'm really looking at double trace bootstrap now analysis. And this was quantified beautifully in this paper by Zohar and Sasha. And the result is that it is negative, so the interaction is attractive as long as delta phi divided square root of the central charge is bigger than this number divided square root of Cj is the central charge of the U1 current. It's the normalization of the 2-point function of the current. Okay, so in free theory, these two quantities are equal. And that's okay, because in free theory, we don't expect what we're doing to apply. We know there is no interaction, there is no interacting superfluid. But what about the interacting theory? Well, now you can plug numbers, and remarkably, we have enough precise numbers to compute this inequality, and it's actually true. And it's true in a very non-obvious way, because this left-hand side is like 0.308, and this is like 0.304 using the numbers. So it's just a funny coincidence. I think more in general, we expect this kind of inequalities to be true based on convexity arguments and so forth, so on. But for the sake of it, we just verified with some number. But okay, that's just a funny game. Okay, so yeah, so just to summarize, what I want to suggest with this slide is that it seems consistent to expect that as you lower J toward the Q square, there is a potential interaction which should collapse your multi-trace state into some new condensed soliton, and we expect it to be what we did before, but of course we cannot prove it at this stage. Okay, so let me now summarize. Yes. I don't know what I would expect. And I was very happy when it was true because we checked it. I don't know. Right, but at the same time, it's not any more perturbative in this interaction. So it would be puzzling. And I would expect something else to apply, but I don't know what. Huh? So the inequality is like if you compute the correction to the energy of a double trace operator with large spin, phi derivative phi, there is one contribution from the exchange of the stress tensor in the 4-point function and one from the exchange of the current. So one is negative and the other is positive. And the question is whether this contribution is negative. This inequality just quantifies this question. You have to compute it from the analytic bootstrap. What? Well, the physical meaning is that so from this picture here, you have particles going on the sphere, and they interact with the potential exchanges between them. And you can argue they are of Yukawa type because there is some non-trivial mapping you can do. And then you're asking, are these Yukawa, the overall Yukawa, attractive or repulsive? And I want to be attractive because I want them to condense when this potential becomes huge. So that's the physical meaning of the inequality. Yes. I think it should be related. Yeah, it's kind of related to some weak gravity conjecture, but okay. Yeah. So okay, I think it's a good moment to summarize. Okay, so what I tried to argue in this talk is that you can get some mileage about the question: what's the lowest dimension operator at fixed charge and spin, at least when charge is sufficiently large or spin is sufficiently large, by using effective field theory. And okay, so you start with some superfluid plus one phonon, and that's what you find. Again, corrections are not shown very precisely in this formula, so take it with a grain of salt, but they are leading order in Q and J correct. Then you have vortices, then you have few vortices, in fact, vortex and the vortex pair. Then vortex distribution, kind of like the vortex lattice you observe for Bose-Einstein condensates. Then we propose that there is a new state, which is a giant vortex state, that naturally interpolates and becomes the Aldheim-Aldacena multitrace picture. Of course, there remain some open questions. Well, the most maybe pressing one, which I think is just technical, is that we have a soliton for this giant vortex state only when the ratio between J and Q is integer or close to be an integer with fluctuations. So there is a Wool regime that all we expect there is that there is some more complicated solution that interprets between two successive giant vortices with vorticity, say, L and L+1, but we were not strong enough to find it. Huh? You cannot trust the single. You have to take into account nonlinearities. It's not an issue with the derivative expansion, but with the field expansion. So nonlinearities become important. So if you find a new, so there is a regime where it breaks down the single phonon. Yeah. So, well, this is all for the simplest CFTs, which are non-supersymmetric, like the O2 model. But, well, with Luca, we showed that there is a lot of interesting physics going on for parity violating CFTs. You can ask similar things in 4 dimension where vortices now are strings, and maybe also for super conformal field theories. I don't think there was much work on the large spin, large J regime. So these are all natural questions. Coming more to more physics, well, to more related question to this single work is like, I told you that there should be some transition at J order Q2 between these many vortices and this giant vortex. The physics of this transition should be that when the rigid body, the superfluids, are spinning faster than the spin of the phonons, there is a phenomenon which is called superradiance, which is just the emergence of tachyons essentially, but which, based on thermodynamic arguments, you expect there to be an instability. I think it's the same phenomenon of Cherenkov radiation. If you have something moving faster than the speed of sound or speed of light in the medium, you have radiation, therefore instability. And at least in Wilkie coupled theories, one should be able to see this explicitly. They saw it in the experiment again, so that maybe in CFT we can see it as well. In general, there are many transitions, order J square root of Q, J order Q, and J order Q square. So what's the order of this transition, the limit where quantum numbers are large? Question? No. So that we don't know. Well, I mean, so you're on the sphere, so there's still speaking no phase transition, but the limit where J and Q are large, you can kind of expect to be there approximately phase transition. So the scaling dimension could have some mild discontinuity in J and Q. So this could be a way to signal that. Huh? What did you say? 30? Yes. Yeah, it could be well. Yes, yeah. The only thing what I'm thinking is that you should be careful with which symmetries are realized, right? So like these states break a lot of space-time symmetries. So maybe assuming emergence of full conformal might be a bit too strong. It's not obvious, but potentially yes. I think actually relatedly in Luca's paper when he studies large scaling dimension, and there I think you can make sharper claims that as you change in the spectrum of large delta and large J, there might be transition which are actually CFTs of one lower dimension. So it could be that a two-dimensional CFT controls the scaling exponent of the phase transition of this CFT, yes? Yes, something like that. It's possible. Or maybe Lifshitz theory again, because we don't know how many symmetries are preserved here. That would be cool if something like this is true. And finally, I think maybe more concrete for the bootstrap is like, as J approaches Q square, I told you we expect some kind of gravitational collapse. And maybe at least assuming some ADS description, say for large C theories, maybe we could follow this gravitational collapse and actually see this large Q regime emerging from some ADS physics that maybe it is more familiar from the bootstrap perspective. So also this would be cool to do in the future. And I think that's all I have to say. Thank you.
Questions? Yeah.
The first slide you talked about was large scaling dimension expansion.
Yes.
Is there any like difference between large and large scaling dimension? I mean, also, like, what is known about large scaling dimension?
Luca is the expert, but I'll give you a quick answer. I think Luca can tell you more, but the idea is that operator, well, I think it's mostly using ETH and Hydra. So you map, well, OP coefficients of operator in between two light operators in between heavy operators to some thermodynamics or hydro correlation functions. And then what you predict is essentially these matrix elements in between some average, some sort of heavy operators. And there is an interplay with large Q and also large J, because now you can look operator with large scale in dimension and large Q, and they correspond to some hydro regime with finite density. I don't know if Luca has more to add.
You could ask a simple question. As a function of delta over J, that large when delta is much closer to J, either all this, that large when delta is close to the twist is close to zero, there like and there should be some kind of conditions where you expect this kind of multi-twist gas to thermalize and to give rise. And so we kind of analogous question.
Yeah.
So related to this, do you think you can take a limit of 4-point function where you scale the external dimension with Q, and then I don't know, there is some regime? So normally you take the external dimension fixed, you go to large spin in the light cone limit, and you can prove the existence of these operators. What if you scale also the external dimension with some as a function of Q? Perhaps there is a regime where you can prove the existence of all this list of operators.
I think the issue with this kind of bootstrap analysis, this was similar to what Sasha we had Daniel Jaffers and Bar Mujanov did in your bootstrap at large charge paper, which I forgot to mention. But yeah, so I think the issue with that is that, I mean, to make some non-trivial predictions, I think you want to have, so you have heavy light channel, and so you can do crossing with the other heavy light channel, or you could do crossing with the light, light, heavy, heavy. The dream would be to do crossing with the light, light, heavy, heavy, and say fix some of these Wilson coefficients and see they're consistent. But this actually, the regime where the light, light, heavy, heavy converges is not the regime where the effective field theory converges. So that doesn't work. You can do heavy light with the other heavy light, and then you can show that at least the superfluid ground state at large Q and small j and the excitation thereof are consistent with that crossing. So that might be, that is presumably can be extended to these large J regimes. Well, maybe, but there is some, I think they argue that it's not too complicated to include spin in that story. So that might be doable, but I think the most complicated thing, which is doing with the other channel and fixing this Wilson coefficient, I think we don't know how to do it yet. Good question. So, okay, so here we have, so there's not much work on Fermi surfaces in CFT, a bit because there are complications with Fermi, because you have a sphere, it's not anymore a continuum momentum. But in free theory, it's rather easy. Well, Fermi surface is just almost free Fermi. So from free theory, it's rather easy to make some calculation. There are some things do not change, so like at least, so this formula here, like this Q2 free half doesn't change, because essentially this follows, you can argue, from some dimensional analysis, but corrections change a bit, and most importantly, excitations change because they are particle Hall pairs. I don't think it's known exact what. While maybe I think we have a picture for some theories that should be superfluid, I think it's less clear which fermionic CFTs will eventually condense to superfluid or become Fermi surfaces. So I think that's maybe what's most missing part. No. So particle vortex duality that I meant here is a trivial exercise. So it's here if you have a scalar, so U1 goes on boson, you can always dualize it exactly to U1 gauge field. There is no assumption about. I think it's still called particle vortex duality, but I'm not relying on the UV particle vortex duality of Paskin and others. And so no, I don't. I mean, even if the theory doesn't have some particle vortex duality, this is still true.
Okay, let's thank Gabriel again. And we start again at 11:30.